Welcome children. Now we are going to discuss some problems from our unit work, energy and power. In our text from page 158 we did the questions 1, 2 and 3. Now listen question number 4. Certain force acting on 20 kg mass changes its velocity from 5 meter per second to 5 meter per second to 2 meter per second. Calculate the work done. See, in a mass of 20 kg, certain force is acting and that force changes its velocity from 5 meter per second to 2 meter per second. We want to find out work done. We know work done is equal to change in kinetic energy. See, work done equal to change in kinetic energy. That is final kinetic energy minus initial kinetic energy. That is half m into v square minus u square. From this relation we can find out change in kinetic energy and it is equal to work done. Work done is equal to change in kinetic energy. That is equal to half m. Here it is given as mass of the body. How much it is given? 20 kilogram. 20 into initial velocity, final velocity. Final velocity is v and initial velocity is c. So v square, that is v is 2, so v square is 2 square minus u is 5, so 5 square. That is equal to 1 by 2 into 20 into 2 square is 4 and 5 square is 25. 4 minus 25, that is equal to minus 21. 2 square 4 minus 5 square 25. That is 4 minus 25 is 21 with the minus. So here we can cancel this 2 and 20, we get it 10. Here it is equal to how much? Minus 210 joule. So the work done is equal to minus 210 joule. This work is negative here because the force is opposing the motion of the body. That means that force tries to stop the body. Because of that, work becomes negative. See, now we can go to, this is the answer for question number 4. Now see question number 5. A mass of 10 kg is at a point A on a table. It is moved to a point B. If the line joining A and B is horizontal, what is the work done on the object by the gravitational force? Explain your answer. That means, suppose here is the point A. Here a body of mass 10 kg is placed and it is moved to another point B. It is C. When it moves from A horizontal. But a gravitational force is vertically down. Displacement is horizontal. Hence the work done here is 0. Work done in this case becomes 0 because force and displacement are perpendicular to each other. Otherwise, here the change in potential energy, if we consider that also we can take as 0 because there is no change in height. Hence the work done in this case also becomes 0. Now question number 6. The potential energy of a freely falling object decreases progressively. Does this violate the law of conservation of energy? Why? The potential energy of a freely falling object decreases progressively. That means potential energy is gradually decreasing. Does this violate the law of conservation of energy? Why? See, when the potential energy decreases, when the body falls, its height decreases, so the potential energy gradually decreases. But you see, at the same time, its velocity increases, so kinetic energy increases. So when the potential energy decreases, kinetic energy increases. Hence, there is no violation of law of conservation of energy. There is no violation of law of conservation of energy because one form of energy changes to other form. So we cannot consider there is any violation of law of conservation of energy because one form of energy is changing to other. Now question number 7. What are the various energy transformations that occur when you are riding a bicycle? When you are riding a bicycle, what are the energy transformations? To ride a bicycle, what energy we getting? That means we eat food. That means from this food we get what is muscular energy. We get muscular energy. That means in food, what kind of energy is present? In the food, there is chemical energy. So, chemical energy changes to muscular energy, and when we pedal the bicycle, this muscular energy changes to mechanical energy. What energy? Mechanical energy. So the energy changes. There is a chemical energy which we get from our food and muscular energy in our body exerting, and that become for rotating the bicycle. So mechanical, and this is the energy transformation which took place there. Chemical, muscular, mechanical. In this way, there will take place energy transformation. Now to question number 8. Does the transfer of energy take place when you push a huge rock with all your might and fail to move it? Where is the energy you spend going? There is no transfer of energy actually taking place because there is no displacement. There is no displacement. Because of that, there is no transformation energy. But when we get fatigue, that means we exert the energy to overcome the friction. We exert the energy to overcome the inertia of the rope, but it is not moving. There is no transformation of energy in this case. Now, question number 91. A certain household has consumed 250 units of energy. 250 units of energy during a month. How much energy is this in joule? The energy consumed is 250 units. That means 250 units means 250 kilowatts energy consumed. Is equal to 250 kilowatt hour. So, to convert this kilowatt hour into joule, we know 250 kilowatt means 1 kilowatt means 1000 watt. So, 250 into 1000 into hour. Into 1 hour is 60 minutes and 1 minute is 60 seconds. So 60 into 60, 3600. By multiplying this part, that is 36 into 25. How much? 5 times 6, 30. Balance 3. 5 times 3, 15. And this 18. 2 times 6, 12. Balance 1. 2 times 3, 6. Now see 0, 10 and this. Once again, 2 times 5, 2 times 6 is 12. Balance of this one is 7. Balance 9. Then 8 plus 2, 10, 9. So 900. Here 1, here 3, here 2. Altogether 9 into 10 to the power 1, 2, 3, 4, 5, 6, 7, 8. 9 into 10 raised to 8 joule. 9 into 10 raised to 8 joule is the energy consumed when we consumed 250 units. 1 unit is 1 kilowatt hour. So 250 unit is 250 kilowatt hour. That is equal to 9 into 10 raised to 8 joule. Okay. Now question number 10. An object of mass 40 kg is raised to a height of 5 meter. An object of mass 40 kg raised to a height of 5 meter. Raised to a height of 5 meter above the ground. What is the potential energy?
If the object is allowed to fall, find its kinetic energy when it is halfway down.
That means we want to find out the potential energy at a height of 5 meter above the ground. And also we want to find out the kinetic energy when it falls from there to a height of 2.5 meter. That means 2.5 meter from the top or also 2.5 meter from the bottom. That two things we want to find out. We know potential energy, that means is equal to mgh. Here m is 40, h is 5 and g is equal to 9.8 meter per second square. So this relation m40 into g 9.8 into h1. See, 5 times 4 is 20. This is 200 into 9.8. By multiplying this 9.8 into 2, that is equal to 19.6. 19.6, then we can put 20. One decimal place also we want to give. That means this is the potential energy, that is equal to 1960. That means this is the potential energy at this height of 5 meter. Potential energy at the height of 5 meter is how much? 1960. When it falls to a height of 2.5 meter, that is half height, its potential energy becomes half. That means 1902 divided by 2. How much it will be? 18, 1, 6, 8, and 7. That means when the body falls, when the object falls to half of its height, potential energy becomes how much? 980 joule. Then what happens to the remaining 980 joule of potential energy? That amount of potential energy now converted into kinetic energy. So the kinetic energy at the half height, that is equal to 980 joule, because the total energy remains constant or same in this case. Hence we wrote potential energy at the half height is 980 joule and the kinetic energy also becomes 980 joule, but the total energy same as before, 1960 joule itself. Now we can go to the next question. Question number 11. What is the work done by the force of gravity on a satellite moving around the Earth? Justify your answer. That means this is our Earth and a satellite is moving around the Earth. See, when we consider the case, here the force is centripetal force. Directional displacement is this way. In this case, force and displacement, they are perpendicular. Hence the work done is 0. That means there is no displacement in the direction of force. Here the force is towards the earth and displacement is tangential. That means it is perpendicular to the force. Hence the work in this case becomes 0. Here the work done is 0. Work becomes
Now we can move to the next question, question number 12. Can there be displacement of an object in the absence of any force acting on it? Think, discuss this question with your friends and teacher. Question once again. Can there be displacement of an object in the absence of any force acting on it? Think, discuss this question with your friends and teachers. That means without any force, can there be any displacement? Answer is yes. In the case of a uniformly moving body, in the case of a body under uniform motion, even though there is no displacement, even though there is no force, there is displacement. That means when a body is moving uniformly, that means if a body moving with uniform velocity, then the force acting on it is 0. But there is displacement. But there is a displacement. So the answer is yes. When does without acting force there is displacement? If a body is moving with a uniform velocity, the net force on it is 0, but there is displacement. So we can consider the answer is yes. Now another question, question number 32. A person holds a bundle of hay over his head for 30 minutes. For 30 minutes. A person holds a bundle of hay over his head for 30 minutes and get tired. Has he done some work or not? Justify your answer. In this case, we know for what? Force and displacement is necessary. That means with the action of force, there should be a displacement. But we consider this case that hay is on his head for 30 minutes, but no displacement. So there is no work. In this case, even though he becomes tired, but there is no displacement, force of gravity is acting vertically downward, but no displacement in this case. So work done is 0. Question number 42. An electric heater is rated 1500 watt. How much energy does it use in 10 hours? See, an electric heater is rated 1500 watt. How much energy does it use in 10 hours? 10 hours. Time is 0. We know
its power is 1500 watt. That is power P is equal to 1500 watt. That is equal to 1500 watt divided by 1000. Now this become kilowatt. That is equal to how much? 1.5 kilowatt. Power 1500 watt, and when we divide with 1000, we know what 1000 watt is 1 kilowatt. So 1500 by 1000 is equal to 1.5 kilowatt. So energy consumed is equal to P into T. That is 1.5 into 10. That is equal to 15 kilowatt hour or 15 units. 15 unit is the energy consumed in this case. Energy consumed in this case is 15 kilowatt hour. That is 15 unit. This is the energy consumed in this case. Now, question number 15. Now see the question number 15 on. Illustrate the law of conservation of energy by discussing energy changes which occur when we draw a pendulum bob to one side and allow it to oscillate. Why does the bob eventually comes to rest? What happens to its energy eventually? Is it the violation of law of conservation of energy? See, this is the pendulum. Now this is in the mean position or equilibrium position. Here the energy now when we consider is a minimum, or we can consider zero. When we displaced this bob to one side, we did certain amount of work, and that work done here becomes its potential energy. Here potential energy alone. See, kinetic energy, here potential energy is maximum. Potential energy in this case, when it is at the point, suppose it is A, it is maximum. At the point A, kinetic energy is 0. When we release this bob, that means this bob is here. When we release this bob here, its potential energy gradually decreases and the kinetic energy increases. When this bob comes to this mean position, kinetic energy, that means energy kinetic becomes maximum, and potential energy here becomes 0. At the mean position, kinetic energy becomes maximum and potential energy becomes 0. Then the bob moves to this side. What happens to its kinetic energy? And this kinetic energy slowly decreases and potential energy increases, and at this position, at the position C, potential energy again becomes maximum. Kinetic energy here becomes 0. And after reaching at this point C, it again moves to this. Then potential energy decreases, kinetic energy increases, here becomes maximum, and then here when you move to here, potential energy maximum, kinetic energy becomes 0. And when this pendulum oscillates or moves, there is some resistance offered by the air, because it is moving through air. So the air offers certain resistance or friction. Because of that, its energy slowly decreases, and in this manner, finally it
comes to rest due to the friction of air through it moves. There is no violation of the conservation of energy, but what happened means here at first potential, then kinetic to potential, and this gradually changes, and why it finally comes to rest means it is due to the friction of air and that energy transferring to in this manner. There is no violation, but there is a change of one form to other form. That is actually happening. Now we can go to the question number 62. See, an object of mass m is moving with a constant velocity v. An object of mass m moving with a constant velocity v. How much work should be done on the object in order to bring the object to rest? We want to bring this object to rest. Its mass m moving with velocity v. We know when a body of mass m moving with a velocity v, its kinetic energy is equal to half m v square. Now we want to bring this body to rest. So how much work here we should do in order to bring this body to rest? The work done in this case is equal to, that means here the work done is equal to the amount of kinetic energy, that is half m v square. So work done, that is become equal to the amount of kinetic energy, so that we can bring that body to rest. See, calculate the work required to done to stop a car of 1500 kg moving at a velocity of 60 km per hour. 60 km per hour. That means a car, its mass equal to 1500 kg, and it is moving at a speed of, that is 60 km per hour. We want to find out how much work we want to do. We know work done here is equal to the kinetic energy. See, this is 60 km per hour, that is equal to 60 into 1000 by 3600. Here 10 times 6, here 6 times. So this 2720 and here 60, that is equal to how much it will come? 100 by 6, that is equal to 50 by 3. We can cancel this again. 5 to 3, 5 to 10, 50, 50 by 3. This is the velocity with which it is moving. So here the amount of work W is W is equal to kinetic energy, that is half m v square. That is equal to half into m, how much? 1500 into v square. That is 50 into 50 divided by 3 into 3. That is here on times 3. Here
5, 50. Now 25. See, 5 times 5, 25. 25 into 25. How much will come? It will come 625. 625 and by 3. This we can divide 2 times 6 in 2, 3 is not possible, so we can put on 0 in 25. How much? 8 times then 3 1 on 3 point something. That means it will come as 2.0833 into 10 to the power 4 joule. This is the amount of work we want to do. That means 2.0833 into 10 to the power 4 joule. That much work we want to do in order to bring that body to rest. Now, question number 82. In each of the following case, force F is acting on an object of mass M. The direction of displacement is from west to east, shown by longer arrow. Observe the diagrams carefully and state whether the work done by the force is negative, positive or zero. See, here is a block. In this case, force is acting upward, displacement in this direction. Here, force and displacement are perpendicular. In this case, force is perpendicular to, here this is the force and this is the displacement. These two are perpendicular to each other. Hence, the work done is 0. In this case, work done is 0. Second one, see, the block is here. Displacement in this direction, force is in this direction. So force and displacement are in the same direction. Force and displacement, they are in the same direction. Hence the work is positive. Here the work is positive. Now see another one. This is the block. This is the displacement. This is the direction of force. See, here force is opposite to the displacement. That means force is occurring in this direction, displacement in this direction. So, in this case, work is negative. Example, frictional force. In the case of friction is a force which is acting opposite to the direction of motion or direction of displacement. Here the work is negative. So, in this case, work is 0, work equal to 0. Here work is positive work. Here the work is negative. Why? Because force and displacement, they are in the opposite directions. Now, question number 91. Sony says that the acceleration in an object could be 0 even when several forces are acting on it. Do you agree with her? Why?
That means acceleration produced in a body is 0, even though several forces are acting on that object. Consider the case of an object. Here, this is the direction of force. Here, another force. Here, another force. Here, another force. When we consider if the net resultant force acting on it is 0, then there will not be any acceleration. So the answer is correct. Yes, it is possible. Even though there is so many force acting on an object, if the net resultant force is 0, then the acceleration produced by that forces becomes 0. Now, question number 21. Find the energy in kilowatt hour consumed in 10 hours by 4 devices of power 500 watt each. 4 devices of power 500 watt. And how much energy consumed in kilowatt hour for 10 hours? That we want to find out. On device 500 watt, in that way there are 4 such devices. So we can take the total power of the 4. Total power of the 4 is equal to 4 into 500, that is 2000 watt. That is equal to kilowatt. 1000 watt is 1 kilowatt, so 2000 watt is equal to 2 kilowatt. 2 kilowatt. And the time that the appliance consume energy is 10 hours. So energy in kilowatt hour is equal to energy in kilowatt hour is equal to power in kilowatt into time in hours. That is equal to kilowatt into 10. That is equal to 20 kilowatt hour or 20 units. That is the energy consumed. How much energy is consumed? 20 kilowatt hour or 20 unit is the energy consumed within this time by the 4 devices of 500 watt each. Now see question number 21st. That one. See question number 21. A freely falling object eventually stops on reaching the ground. What happens to its kinetic energy? When a body falls freely, we know what is actually freely falling. When a body falls under gravity alone, if a body falling under gravitational force alone, then it is under free fall. Now, when a body falls, what happens to its potential energy? Its potential energy gradually changes to kinetic energy, and when the body is just going to touch the ground, height becomes 0. When the height is 0, its kinetic energy becomes a maximum. Kinetic energy becomes a maximum, and there is no potential energy. when it strikes the ground, after that there is no kinetic energy. Then what happens to that kinetic energy? That is the question here asking. This kinetic energy, when it strikes the ground, that changes into different other forms. A part of it becomes sound because we can hear falling sound. A part of it becomes heat energy. That means when the body falls to the ground, there will produce a small amount of heat. Then a part of the energy can be changed to what is produce vibrations of the molecules in the ground. In this way, kinetic energy changes to sound. Sometimes there may produce some light also. So it can change mainly what is sound, heat, and sometimes there will produce what is light, and sometimes vibration. In this way, that kinetic energy changes. Now with this all, we discussed all the questions given in our exercise. So from this unit, we know what are the things actually work. Work depends on two factors called force and displacement. There are two different types of work, force, that is positive and negative one. Then we discuss about different forms of energy. Among that one is mechanical energy. This mechanical energy is of two types, potential and kinetic. Then we discuss about rate of doing work or speed of doing work, and it is termed as power, and its unit is watt. Then also we discuss about conservation of energy. What it says energy, we can transfer from one form to other, but we cannot destroy or produce energy, but only we can transfer from one form to energy to other forms. With this all, we can wind up today's class. Okay, thanks.